Okay, so get this. 9 out of 10 students, yeah, literally 90%, mess up binary and denary conversion on their exams. And the worst part? It quietly wrecks their overall grade. It's not because they don't understand computers, right? It's actually because they fall into this incredibly specific, sneaky formatting trap. So let's dive right into this explainer. Today, we're treating this like a full-screen, high-def classroom. We're not just going to sit here and memorize textbook facts. No way. We're going to decode the exact mechanisms of Cambridge IGCSE Computer Science. We'll start by looking at this massive failure point, and then we're going to build a bulletproof framework so you absolutely never make these generic mistakes again.
Take a look at this classic, flawed answer we've got here on the left. You see a student trying to convert a binary number by just kind of eyeballing the digits, guessing the output, and leaving literally 0 working out on the page. And then, bam, a dramatic red pen correction strikes right through it. Look, the examiner isn't looking for magic here. They're looking for your method. We've got to diagnose this exact error right now so you never, ever make it. Skipping the column headings? That is the #1 reason students hemorrhage marks here. You absolutely have to show that machine-level logic. To really understand why this mistake happens so often, we kind of have to rebuild our foundation of how computers actually process data. The Denary system is what we humans use every day. It's base 10, counting from 0 to 9. But computers? They couldn't care less about our numbers. They rely entirely on the binary number system, which is base 2. Why? Well, because at the absolute lowest hardware level, a processor is just made up of billions of microscopic transistors. And these transistors can only hold an electric charge, which we call a 1, or no electric charge at all, which is a 0. It's literally just electrical on and off states. That's the whole shebang. So how exactly do we correctly translate those tiny on and off states into a number that actually makes sense to us? You build this 8-bit table. Seriously, this thing is your ultimate weapon. The binary heading values just double each time as you move right to left. 1, 2, 4, 8, 16, 32, 64, and 128. It's that simple. By mapping a binary number like 10011 right under these specific column headings, all you do is add up the columns where the electric charge is switched on, meaning where there's a 1. So here you can clearly see that 16 plus 2 plus 1 equals 19. Writing this table out on your paper effectively destroys that common exam trap, and it secures your method marks every single time. Okay, so now that we've totally cured that specific binary calculation error, we really need to tackle a systemic problem that pops up across all theory topics. Check out this brilliantly illustrated framework. It completely solves the issue of giving generic answers across topics like input, output, and storage. See, most students just memorize a device's name, but then they completely freeze up when they're actually asked to explain how it operates. To secure those top grades, you've got to train your brain to transition through 3 very specific layers of understanding. So, here is your 3-layer learning path. Layer 1 is what we call simple context. This is just using everyday casual language to understand the basic practical problem a concept actually solves. Next up is Layer 2, technical vocabulary. This is where we strip away those casual words and replace them with precise, hardcore subject terminology. And finally, we hit Layer 3, exam-style shaping. This whole path guides you from just understanding the everyday purpose of something straight through to formulating a really concise, high-scoring response while you're under the intense time pressure of an exam. It's all about shaping your knowledge to perfectly fit the mark scheme. Notice how beautifully you can apply those exact layers to complex hardware topics, like the central processing unit. Say an exam asks why a computer is underperforming. If you just stick to Layer 1, you're just saying, oh, the system is slow. But guess what? That scores exactly 0 marks. Layer 2 steps it up by introducing the technical vocabulary, identifying key components like the ALU or registers. Then, Layer 3 shapes it for the win. You formulate a timed, punchy response detailing the fetch, decode, execute cycle, and exactly how clock speed or cache size impacts instruction processing. You're literally shifting your brain to use precise mark-earning terminology. And you know what? You can apply this exact same visual method to abstract networking concepts too. The internet structure isn't just some invisible magic in the sky. It's a very real series of physical and logical handshakes. By using everyday language first, like, say, comparing a router to your local postal sorting office, you build that essential foundational context. Then you step up to the rigorous demands of the exam by utilizing what we call the 4-question framework. Just ask yourself, what is it? How does it work? Where is it used? And why does it matter? If your answer hits all 4 of those, you are absolutely golden. So the really crucial point here is understanding those distinct Cambridge command words.
Examiners use very, very specific verbs, and if you misinterpret them, you're going to lose out big time. You simply have to know the difference between a description and an explanation. A description just states what a process or device is, like just naming a networking device. But an explanation, that details exactly how it works and why it actually matters. Like detailing the exact sequence of a router determining the most optimal path for data packets. You absolutely have to provide that sequence of mechanisms to get full credit.
All right, let's pivot over to data integrity and see how this framework builds up. When transmitting data, computers have to interpret formats perfectly. A check-digit mismatch is basically the primary indicator of a transmission error. If you mix up your key terms here on an exam, it is going to cost you heavily. This is especially true when we're talking about how computers ensure the data they just received is actually correct and usable. Whatever you do, never confuse these two terms. I know they look incredibly similar, but in the world of computer science, they are entirely different defense mechanisms. Validation is an automated reasonableness check run by the computer itself. Like, making sure a date of birth you entered doesn't imply you're 300 years old. Verification, on the flip side, requires human or secondary system intervention. It purely ensures that the data was accurately copied or entered from its original source without any typos, often using something like double entry. You need to know this distinction cold. To really secure those full marks on application questions, we have to master a crucial technique called contextual anchoring. Let's say you're asked to explain the use of registers or memory. You cannot just spit out a textbook definition. You have got to anchor your technical explanations to the specific digital scenarios they give you in the prompt. If the exam question mentions a robotics lab, a smart home, or even a retail store barcode scanner, your answer must explicitly link the hardware's function right back to that exact real-world setting.
So how do you actually practice this anchoring? Well, you use the 3-pass revision cycle. Pass 1, you secure your basic definitions and contrast them against similar terms, like understanding memory versus storage. Pass 2, you rehearse step-by-step worked explanations, literally writing out the sequence of operations. And finally, Pass 3, you adapt those explanations to totally new scenarios. By actively cycling through these 3 steps, you transform a really basic, fragile recognition of a topic into a high-level, adaptable application that examiners absolutely love to see.
Okay, before you finalize any long-form answer, I want you to run it through the 4-question filter you see right here. Think of it as a strict quality control scanner for your brain. Did you clearly identify what the device or process is? Did you explain step-by-step exactly how it works? Did you justify why it's used in the specific context? Because, listen, if you missed the how or the why, you've completely left the logic and mechanisms out of your answer, and you are just leaving easy marks right on the table. Let's put this into practice. Take a close look at this fresh, deeply flawed answer. The question asks how a specific network device operates in a retail store. The student wrote, "It connects computers together and keeps the data safe." Now, the timer is ticking. I want you to use our new framework to spot exactly what is missing here in the next few seconds. Ask yourself, why on earth would an examiner give this 0 marks even though the statement is generally true? All right, time's up. The glaring problem there was super vague wording and absolutely 0 context. Notice how the expert correction upgrades the answer entirely. It replaces those vague labels with extremely precise technical terminology. It explains the clear, logical sequence of exactly how packets are routed. And, most importantly, it anchors the mechanism directly to the provided scenario of the retail store's point-of-sale system. It moves completely from a generic Layer 1 guess to an absolute Layer 3 masterpiece. Shape the idea into a concise, high-scoring answer designed for time pressure. This quote beautifully captures the entire philosophy of Layer 3 learning. You're not just blindly memorizing facts from a textbook, crossing your fingers and hoping the right question comes up. No, you are a tactician now. You are actively shaping your knowledge to beat the exam constraints. You're learning exactly how to compress complex technological sequences into tight, high-scoring bullet points that are engineered to satisfy the exact demands of the syllabus. As we wrap up this explainer, I really want to leave you with a direct challenge. The next time you sit down to study, please don't just read. Master the mechanism, anchor it to a real-world scenario, and aggressively use that 4-question self-check. I challenge you to apply this exact 3-layer framework to the very next microtopic you revise. Ask yourself, are you just describing things or are you truly explaining them? If this breakdown made the logic finally click for you, make sure you dive into our next explainer to keep building up that technical muscle. After all, if you can decode the exam logic this easily, what other complex systems are you capable of reverse engineering?